Hello and welcome to this lecture on models of a fluid at rest.
So as I had explained in the first part of this lecture at the last slide, post recording, because of the overall length of the whole lecture, I decided to split it into two parts. So in the previous part, we sort of developed the model of the ideal gas equation of state from thermodynamic perspective, which is considering the entropy. And also we partly developed the model of an ideal gas equation of state from the kinetic energy perspective, transport perspective. We connected those two, and from there we sort of obtained relationships for internal energy of the ideal gas and enthalpy of the ideal gas. And we are going to look at the various thermodynamic properties of the ideal gas going forward.
Now we are going to look at specific heat capacity of an ideal gas. Specific heat capacity of an ideal gas is the amount of thermal energy added to 1 mole of a gas for increasing its temperature by 1 unit. The system does not exchange energy, adiabatic boundary, or it's an impermeable boundary also. So the question is basically whether the volume is constant or pressure is constant. So when volume is constant, the appropriate energy of the system is internal energy. When pressure is constant, the appropriate energy of the system is enthalpy. And Cv therefore is dou u dou T at constant V. And for 1 mole of a system, so N is fixed to be 1. And therefore this is simply F by 2R. And Cp is dou H dou T at constant pressure. And N is fixed to be 1. This is F plus 2 by 2 into R. Keep in mind, therefore, that Cp minus Cv, the difference would then be simply R, which of course was shown to be in a general expression Tv beta square by kappa T, where V is molar volume, V by capital N. So for various gases again, ideal gases, monatomic, diatomic, triatomic, the specific heats are given in this table. Now we look at the expansion and compression properties of an ideal gas. Coefficient of thermal expansion is defined by 1 by V dou T at constant pressure. V is RT by P, therefore dou T at constant pressure is simply R by P, temperature being in the numerator. So beta is simply 1 over temperature. Isothermal compressibility is minus 1 by V dou P at constant temperature. And V is RT by P, therefore dou P at constant temperature is minus RT by P square. And but RT is then this can be simplified, so substituted here, and then you can write RT to be PV, and the V will get cancelled, and then kappa T is simply 1 over pressure. So beta by kappa T is simply P over T or R over V. Joule-Thomson coefficient is given by V by Cp into T beta minus 1, but T beta is 1, and therefore Joule-Thomson coefficient is 0. Now you can also obtain an expression for adiabatic compressibility. I will leave that to you to work out isentropic compressibility for an ideal gas. Note, while we are looking at why Joule-Thomson coefficient is 0 for an ideal gas, enthalpy is a function of only temperature. Therefore, when I'm saying I have an isenthalpic process, temperature cannot change. So therefore, T has to be constant, and therefore Joule-Thomson coefficient, this partial derivative, must become 0. Now we look at what is the change in internal energy and enthalpy of an ideal gas due to a process Change in internal energy as a function of temperature and volume, U expressed as a function of T and V. Notice that beta by kappa is basically P by T, and therefore this term drops off. Du is Cv dt, which of course should be the case because U is a function of temperature alone. And similarly, change in enthalpy of an ideal gas is given by Cp dt plus V into 1 minus beta T times dV, but beta is 1 by T, and therefore this term will vanish and dH will be Cp dt, and enthalpy is also a function of temperature alone. So these can be integrated to get change in internal energies and change in enthalpies, and this is one of the most commonly used expression for getting changes in enthalpies and internal energies of ideal gases. So if you know the specific heat capacity as a function of temperature, there are a number of empirical relationships that are obtained, starting from taking these two to be constants, or taking this to be a linear functions of temperature or a quadratic functions of temperature, and so on and so forth. So they are often used in energy balance calculations. Heat capacity ratio. Heat capacity ratio, or often also called as adiabatic index. This gamma is a ratio of the specific heat capacity at constant pressure to that of constant volume. Now, so what does this mean really? Of course, before we look at the physical significance of gamma, we notice that this is F plus 2 by 2 nRT, F plus 2 by 2 times R, and Cv is F by 2 R, and therefore gamma is simply F plus 2 by F, where F is the number of degrees of freedom available for the ideal gas. So for a monatomic ideal gas, you will have a certain number, diatomic ideal gas, you will have a certain number, and so on and so forth. Now, consider an experiment on a closed pneumatic cylinder containing an ideal gas. By closed, this means that the ideal gas cannot leave the system, so the boundaries are impermeable. A piston covers the cylinder and seals the gas and is at a locked position. So this is how we start the process. Now initially let the pressure inside the cylinder equal the atmospheric pressure. Then we add thermal energy to the ideal gas, say by heating the system. And the gas temperature is raised to a preset temperature. Now since the piston is locked, the volume is fixed, and therefore the energy added is simply Cv times delta T. Of course, here it has been assumed that Cv is constant, independent of temperature rather. Otherwise, this would be integral Cv dt. Now, we take the piston and cylinder to be well insulated, in other words, to be adiabatic boundaries. Alright, so there is no heat loss. This means both the temperature and pressure of the gas will increase. However, the volume will remain constant. There is more kinetic energy, and therefore the gas molecules will go exert higher pressure on the walls of the system, which is walls of the piston and the cylinder. Once the preset temperature is reached, the piston is now free to move. Now the next step of the process unfolds, where one of the boundaries, which is that of the piston, is a moving boundary. Since the gas pressure inside the piston has increased beyond the initial pressure, which is the atmospheric pressure, so the internal pressure at the piston boundary is greater than the external pressure, which is the atmospheric pressure. So the gas will expand, the piston will move outwards. The piston will move outward until the internal pressure reaches the same as the external pressure, until you reach mechanical equilibrium, which means both pressures are equal to atmospheric pressure. This expansion is an adiabatic expansion because the piston cylinder system is still perfectly insulated. So this expansion will cause cooling of the ideal gas inside the system, and its temperature will drop below the preset value, right? So this is to be expected. To raise the temperature to the preset value again, additional thermal energy should be supplied. This is a reversible process altogether. This energy is equal to the work done by the gas in displacing the piston so as to maintain its pressure and thereby maximizing the entropy. So how much cooling has happened? Where did that cooling why did it happen? Basically, the gas did work to move the piston to the position, new position where there was mechanical equilibrium. So that energy was taken from the gas, and that since the gas being an ideal gas only has kinetic energy, and therefore its temperature has to drop. So the total energy supplied, if you were to bring the temperature back to the preset value, now what you have essentially done is, now the new state of equilibrium is where the pressure is constant, not the volume. The volume increase, isn't it? So the total energy supplied now is Cp delta T. So what is the extra energy that was supplied? The extra energy that was supplied from Cv delta T to Cp delta T, right? From the constant volume system case to the constant pressure case, the extra energy supplied was the work done in displacing, right? The work done by the gas to displace the piston from its original position to the new position corresponding to mechanical equilibrium and thereby pressure being held constant. So that P delta V is the energy that has been additionally supplied. Okay, so the difference therefore you can see is Cp minus Cv is going to be R, because P delta V is R delta T, right? So and the ratio of these two energies is gamma. So one is Cp delta T, the other is Cv delta T. The ratio of these two energies is gamma, is the heat capacity ratio. So for an ideal gas, you get gamma as F plus 2 by F, that is 5 by 3, 1.66. For a diatomic gas, it's 1.4. And for a triatomic gas, it is roughly 1.29. So we now look at adiabatic or isentropic processes with ideal gases. So for a reversible adiabatic process, there is no heat exchange. Entropy is constant, ds is 0. For an irreversible adiabatic process, there is still no heat exchange, but ds is greater than 0. So using molar properties, du is TdS minus PdV. TdS is 0, and therefore du is minus PdV. dH is VdP. We are looking at fixed 1 mole of ideal gas. For an ideal gas, U is a function of temperature alone, H is a function of temperature alone. And we know that du is Cv dt, dH is Cp dt. And so we can equate these two, right? The heat capacity ratios, gamma is Cp by Cv, and so therefore Cp by Cv is simply minus of Vdp by Pdv. So this expression can be obtained, and this is a constant. So therefore we can separate the variables and integrate. Separate, now we have on the one side only functions of pressure, on the other side only a function of volume, and so you integrate this and this should become a constant. So this basically gives the expression PV power gamma is constant, and this is the PV path, pressure volume expansion contraction compression path the system will take, an ideal gas will take when undergoing an adiabatic process. So the following relations also arise by recognizing that PV is equal to RT. This is V by N, so the N has come to the denominator and this has become small v. So PV is simply RT, right? Recognizing this, we can also obtain the same expansion compression processes, adiabatic processes of an ideal gas can be described using a TV relationship and a PT relationship. All of these are interrelated by simply substituting these inside, and eliminating one variable over the other. You can obtain all these relationships. Now we move on to entropy of a monatomic ideal gas. So for this, we start from the internal energy, U is 3 by 2 nkt, or in other words 1 by T is 3 by 2 nk by U, and molar internal energy is internal energy per unit molecule now we are defining as U by capital N. And similarly, P by T is Nk by V, and I now notice that these small u's and small v's are not molar quantities but per molecule. Keep in mind. Gibbs-Duham relation gives the relationship between the intensive properties Tp and mu. In the entropy formulation, this relationship is simply U into d of 1 by T plus V into d of P by T minus N into d of mu by T is equal to 0. So for a fixed number of molecules, if you divide throughout by N, so where you use U by lowercase u is U by N and lowercase v is uppercase V by N. So then this d of mu by T is, this can be taken to the other side, and then lowercase u d of 1 by T, okay, I'll come back to this in a moment, and lowercase v times d of P by T. Now what has happened here, 1 by T is 3 by 2 k by U, and P by T is simply k by V, and those have been substituted here. So now when you are taking a differential with respect to U, then this becomes minus 3 by T k by U square du. Similarly, when you take a differential of V, then this becomes minus k by V square dV. So d of mu by T is simply minus 3 by 2 k du by U minus k dV by V. For a fixed number of molecules, we got this expression for change in mu by T. We can integrate this expression and we would get mu by T minus mu by T naught. So for an initial state of mu by T naught and corresponding initial internal energy to be U naught and corresponding initial internal energy per molecule being U naught and corresponding volume per molecule to be V naught. So this is not volume of a single molecule, by the way, just keep in mind, okay, that is negligible. This is volume occupied by a single molecule. So if you have a total volume capital V and there are n molecules, so essentially what is the volume that is occupied by a single molecule? Okay, so it is that kind of a picture, not the volume of that sphere. This sphere that is indicated, that I've been using the laser pointer to describe as a rigid spherical molecule. It's not that volume. It is volume. This volume divided by the number of molecules. So the initial case of volume being V naught. So we can integrate this to an initial condition, right? And then we have regenerated this with respect to this U is U by capital N, this V is V by capital N, and therefore together that becomes pi by 2 ln of N by N naught. Here U naught, V naught, N naught are parameters of a fixed reference state, and mu by T naught is an undetermined constant of integration because you don't know what the initial chemical potential is. From Euler's integral fundamental relation, S is U by T plus PV by T minus mu N by T, and therefore we can substitute the expression for mu by T here, okay, and U is of course 3 by 2 nRT, or sorry, capital NKT, and V is PV is NKT, so all of this can be substituted and we can get an expression for entropy where this initial condition of chemical potential, which we don't know, is lumped with the 5 by 2 K that comes up as a constant, and that is the initial entropy of the system, which we don't know. So of course this expression is fascinating because it reveals a lot of things about entropy and its relationship between UVN, but it is not very practical simply because this constant is unknown. Okay. Now let's try and understand what we are able to gather from this relationship for entropy of a monatomic ideal gas. Since U is 3 by 2 nkt, as temperature tends to 0, we know that entropy should tend to 0. There is no kinetic energy for the molecules. All the molecules will be in their frozen positions, but no potential energy of interaction. So there is only one way in which that state can be created. That multiplicity will be 1 and the ln of W will be 0, S should be 0. Okay. So by the way, here what has happened is instead of U being kept, we have substituted U is equal to 3 by 2 nkt and expressed S as a function of TVN, because now we want to sort of look at this relationship of entropy and temperature. So as T tends to 0, S should tend to 0. But as T tends to 0, what does this expression predict? This expression predicts that S will be given by ln of 0, which will be negative infinity. So the point of 0 entropy is not where temperature is 0, but wherever this quantity becomes 1. Right? Wherever the quantity in the square brackets becomes 1, that is where entropy is becoming 0. Not where it should, which is at temperature tending to 0. So from this we can conclude that this expression of an entropy of a monatomic ideal gas is a good approximation only when the argument is much larger than 1. When you get close to 1, you start seeing deviations. And this of course would occur when V by N, so this is V by n power minus 3 by n power minus 5 by 2. So if you can take one of the n's out here, so if V by N is very large, or the density of the gas is very small, one can ensure that this argument of the logarithm will be large enough. So one of the conclusions is that while this is a very interesting expression for entropy, all right, even if it is only to an integration constant, this expression is valid only when the assumptions that we set out in deriving the model for an ideal gas, when only those assumptions are valid, is this expression valid. Otherwise, this is not valid. So even though we have not been fully successful in estimating the entropy of an ideal gas, we can estimate change in entropy of an ideal gas. And changes in entropy of an ideal gas may be obtained in other ways, for which we already have ds Cv by T dt plus beta by kappa T into Tv. So for an ideal gas, beta by kappa T is R by V, and therefore if your Cv may be treated as a constant independent of temperature, then you can get change in entropy is given by this expression. From one state to another state. Of course, we can only not get the initial state's entropy. That is the only deal, which is what we found out even in the previous expression. Similarly, we can write change in entropy as a function of temperature and pressure. And beta is 1 over T, and therefore beta V is V over T, and that is R over P. PV is RT. So we can integrate this again, taking Cp to be independent of temperature. Okay, we get this expression, and therefore these two are identical to each other, and I would leave you to determine that. Now the next one is Gibbs free energy and chemical potential. To obtain the chemical potential for an ideal gas, we will rewrite entropy in terms of temperature and pressure rather than internal energy and volume, because we need to get Gibbs free energy also. Substituting U is 3 by 2 nkt, and letting the constant S naught is some ln of some arbitrary constant phi, and using P by kt is n by v, we get a much simpler expression where that n times S naught has been taken into this logarithm itself. So it's just a constant, so this is much easier to manipulate. Now G is U plus PV minus TS or H minus TS. So therefore, we have to look at U plus PV is enthalpy, which is for a monatomic ideal gas, 5 by 2 nkt. All of this is for a monatomic ideal gas so far. And then minus T into S. So the T is here, so minus nkt into ln of this term. Chemical potential is partial molar Gibbs free energy at constant temperature and pressure. So this logarithmic term does not have any n in here. The n is here at the outside. So the chemical potential can simply be obtained as 5 by 2 kt minus kt times ln of this term, the temperature term, plus kt ln of P by P naught. Here it is P naught by P, and that is flipped to P by P naught, and therefore the negative sign has been made into a positive sign. Notice that these first two terms are a function of temperature alone, and therefore they are called mu naught of T plus kt ln of P by P naught. So for any initial state to a new state, the change in chemical potential is mu minus mu naught. Okay, that is given by kt ln of P by P naught. And so this part is taken to be mu naught of T, and this is basically for the initial state mu of T comma P naught. Okay. Therefore, one can write an expression mu is mu naught of T plus kt ln P by P naught, and this is a very important expression in all of thermodynamics of phase equilibria and reaction equilibria, right? So this is an expression for chemical potential in terms of temperature and pressure. Mu is a function of temperature, pressure. For polyatomic ideal gases, you would notice that the only difference is going to be, instead of 5 by 2, you're going to get 7 by 2. 7 by 2, you're going to get 9 by 2, and therefore only the mu naught of T differs. This expression still holds, and therefore, without having to go through any of these derivations again, we have obtained the expression for chemical potential of an ideal gas, monatomic, diatomic, triatomic, polyatomic, doesn't matter. So to summarize, this has been a very long lecture. What have we done? What have we accomplished? We developed a model for an ideal gas, primarily from the thermodynamic or entropic perspective, but we started out with the kinetic theory perspective. We sort of connected the two, and the model equation turned out to be a PVT relationship, which was the ideal gas equation of state. We obtained the ideal gas equation of state. From there, we developed expressions for the thermodynamic potentials. Now, at the end, we can see that we have developed expressions for internal energy, enthalpy, and Gibbs free energy of the ideal gas. We developed an expression for entropy of an ideal gas. Of course, we needed this to obtain the expression for Gibbs free energy. We estimated then the various thermodynamic properties, specific heat capacities, heat capacity ratios, PVT relations for adiabatic processes involving ideal gases, coefficient of thermal expansion, isothermal compressibility, and I have asked you to evaluate for yourself what isentropic compressibility is, Joule-Thomson coefficient, changes in entropy of an ideal gas, and chemical potential. So all this thermodynamic framework that we have developed so far is general enough that you take one model for a system, and you can just go right through from the beginning to the end and obtain all these thermodynamic properties of that particular system. We have shown that for an ideal gas, a single component system. So for each such model of the system, whether it is a gas or a liquid or a solid or mixtures, multiple phases. In fact, the next part of this lecture is going to go through the same thing for mixtures. Of course, we will not have the initial part of developing the ideal gas equation of state. We will just modify the equation of state for mixtures and go right through all of this, right? So for gas or liquid or solid or mixtures in multiple phases of them, the thermodynamic framework developed so far can be used to determine thermodynamic properties and conditions of equilibrium. What are the rest states, end states, given the criteria for thermodynamic equilibrium, especially for phase and reaction equilibria. You take the expression for chemical potentials and build from there, right? So this is sort of the summary of what we have done so far, right? This summary also encapsulates what we have done from the first lecture on thermodynamics. So we developed the framework and we employed the framework to demonstrate to you, how that frame, with one model of an ideal gas, how we can obtain all these thermodynamic properties of that particular system. So this brings us to the end of this lecture. It's a long lecture again. I'm sorry that this is long, but this is one chunk that has to be communicated together, and therefore it has been done so. So I urge you to please take your time looking through these the whole lecture in parts, so to speak. The kinetic theory part, the entropic part, and then the internal energy, enthalpy part, heat capacity ratios, and the various compression expansion properties part. And then we come back to deriving expression for entropy of an ideal gas, changes in entropy, and then Gibbs free energy, chemical potential, right? So many parts are there. I urge you to please, if you have to rewatch it part by part, so that you can put all the pieces together and get this big picture. So I would be, as always, very happy to take any questions you may have. I would be very happy to address any clarify any doubts you may have, and I would always welcome feedback from all of you. You can always reach out through my YouTube channel, or my email ID is available in my website, which is the link for which is available in the about part of the page of the YouTube channel. Or if you're already a student of mine in one of my courses, you have other ways to access me as well. All right. With that said, thank you very much for listening to this lecture. I hope you have a wonderful day. Thank you.